Good afternoon, everyone. Can you hear me okay? Good. I was worried there for a minute. Thank you. Um, okay, get the slides shared. There they are. Okay, so last time someone asked about quiz 3 and if it would be due on Monday, even though that's the President's Day holiday and the class is canceled. And I said that I would postpone it. So I've postponed it till Wednesday at 3:55. So you have now 1 week to take quiz 3. Make sure you take it before next Wednesday at 3:55. And like I said, if you find any issues with the quiz, let me know. Okay, so last time we covered stability. I mentioned that there's different ways that you can determine if a system is stable. A system can be a standalone system, a standalone component, or it can be a system comprised of multiple LTI systems linked together, as you would have in an open loop or a closed loop control system. I mentioned that the impulse response is a good way to determine if the system is stable. And so to verify that, you can simulate the impulse response in MATLAB, or you can do the inverse Fourier transform and plot the resulting time domain function. And to do that, you have to calculate you're basically calculating the eigenfunctions of the system, which I showed you how to do that. And of course, you can also use the step or a step function, a step response. But the step response, typically you would do that in software. But in this class, we're going to focus on number 2, which is to find the poles. The poles are just the values of S that would make the denominator 0 in the transfer function. And we will also use this method in the Z domain, which we will get into today. So in this class, basically stability, mainly you're going to solve the stability through looking for these poles, because you can just work that out on paper. Okay, so this slide shows how to find the poles. In this case, we had a system, a transfer function that was S divided by S plus 3 times S minus 2. The poles are at S equals minus 3 and S equals 2. We're looking for the system to be stable. The poles would have to be in the left-hand plane, meaning that they would have to all be to the left of the imaginary axis. In this case, that's not true, because we have S equals positive 2 as a pole. And so I showed you last time how to, and I think the lecture before that too, we ran through this, where you can decompose the function to put it into a form that you can do the inverse Laplace transform, and then convert it back to time domain. And then in this case, I'm just plotting the time domain. I just plotted this in MATLAB versus time, where in this case I varied time from 0 to 10 seconds. And you can see that it diverges in an unbounded way. And then I showed this is the step response and of the same function, and this is a sinusoidal response. And then I basically just changed, I kind of arbitrarily tweaked the function a little bit to make it so it's stable by changing where the poles are, and I did that by just changing the denominator. So instead of S plus 3 times S minus 2, I just changed the S minus 2 to S plus 2, and that allowed me to move the poles to the left-hand plane of the pole 0 plot in order to ensure that the system was stable. So basically, that's really kind of what that's kind of an aspect of control theory, is when you're designing a controller. That's really what you're doing in a way, is that you're just making sure those poles are in the right spot. Now, the problem is, I mentioned this last time, is that just moving the poles often isn't enough, or isn't a great way to do it, because even though the system may become stable, it's not necessarily going to be a good controller. You know, it may not work well in practice. And we're not going to talk too much about that. Also, notice that I'm basically, in this case, the way I moved the poles was I modified the transfer function. In a real control system, you would not be able to manipulate the transfer function of the plant. You only have control of the transfer function of the controller, but you have to keep in mind that you would have to change the controller transfer function in a way that, when multiplied against the plant, and then of course, you know, also incorporated into the closed loop transfer function, that the poles of the closed loop transfer function will be moved. So it's a little bit, in practice, it's a little bit more indirect in the way that I'm doing it. And there are procedures to build controllers that basically allow you to change the pole locations of the complete closed loop transfer function. But again, we're not going to cover that. In this case, I just moved them in the, you know, basically in the plant, which, like I said, is not you know, something you couldn't do in practice. You can't change the plant this way. But I just wanted to show you how changing the poles in a transfer function will make it stable by doing that, and then of course doing the inverse Laplace transform. So then I showed you some more pictures of that. Then we talked about transfer functions. Transfer function is when you take an S domain LTI and you structure it so that it is a ratio of the output divided by the input. So this is really just all about using algebra to rearrange the expression to get it into this transfer function form. And this is what ends up giving you essentially input and output ports on these LTI systems. I think this is pretty neat how this works. And I also like how, you know, it's all just comes down to algebra and rearranging the equation and multiplying polynomials. It makes it pretty easy. Then I talked about a physical system. So this is where we came up with a simple physics problem, which is basically a system where you're applying a force to move an object, and so the input is the force and the output is the position of the object. And so we worked that out. We started with a partial differential equation and then converted it to the S domain through a Fourier transform, and then we converted it to a transfer function by just, you know, rearranging the terms. We ended up with a transfer function that was 1 over m divided by s times s plus b over m. This transfer function is unstable because there's a pole at 0. And so in order to stabilize it, we would have to, you know, multiply it against a controller transfer function to get an open loop transfer function. And then optionally, we can also do a closed loop transfer function as well to make a more robust controller. Coefficient, did I misspell that? Oh, friction, yeah, sorry, thank you. Friction, should say friction. That was an autocorrect. Thank you. Thank you. Coefficient of friction, yep. Okay. Yep. So that was that. Now, by the way, if in case you're curious, you might be wondering, like, what if you're trying to control something that you can't derive an LTI system for directly? You know, there actually are ways to do that. It's called system identification. You can have a black box, for instance, like a system, like say a robotic arm, for instance, and you don't really know how it works and you don't know what's inside, but you want to know what its transfer function would be as a plant. So you can actually, there's methods where you can, if you send in a sinusoid input signal and look at the output, you can sweep the frequency of the input and use that to construct the frequency response, and then convert that to a pole 0 plot, and then use that to construct a transfer function. So you don't actually have to build plant models this way. You can also build a plant model through a system identification approach. So this is what's called, this is a, what I've done here in this slide is I've used a glass box method where you know how the physics work based on the first principles, which generally are going to be like Newton's laws, and then you build the system, the transfer function that way. Another approach is a black box method where you have this device or this object and you hit it with some input stimulus and you measure its response. So that's another way to do it. There's two main ways to do it. So I showed the step response. That was, you know, not really helpful because we know it's unstable. Also, it kind of makes sense too. I mean, think about it. If you apply a force of 1 Newton at 1 second and just keep that force on, obviously it's not going to stabilize. So that all makes sense. Then I talked about the closed loop control. And what this is really all about is building a more robust controller that can monitor the output of a system and make adjustments. And in this case, specifically, we're trying to get the system to output a certain set point or to behave at a certain set point. So this would be a cruise control, autopilot, you know, any sort of system where you're trying to control it to a set point. And the neat thing about this closed loop system is that I had to work through the math a little bit to get there, but basically you end up with a very classical sort of well-known closed loop control transfer function, which is essentially just the open loop transfer function, which in this case is the plant times the controller because there's only two things in there. And then you divide that by 1 plus the open loop transfer function, and that'll give you the closed loop. And that's assuming that you're using the you know, basically the differencing block in there, where you take the output of the plant and you take the difference between that and the R reference, which is the set point. So as long as your closed loop system is in this form, you can just apply this closed loop transfer function, which is pretty neat. And it doesn't have to be exact. You know, like I said, you can have more. Your open loop transfer function might look different because it may have more things, or it may even be nested. But this is the, you know, like I said, this is basically just your classic closed loop control transfer function. Now, again, though, as you might imagine, in order to work this out, you know, you have to do some algebra. You have to do the multiplication and then work it out to get the S domain transfer function into a nice ratio of two polynomials. Okay, so then we talked about a PID controller. This is only one type of way to build a controller. This is the simplest one. It's the one that you guys, I think, are familiar with from robotics. I'm not sure how they covered it in there. I don't know if they did it formally like this or if it was more of an ad hoc sort of way to do it. But PID controllers are kind of a basic way to build a controller. More advanced controller techniques usually require a state space controller, which there's some ones, and generally speaking, those ones are I can't remember the name, QLR controller. There's other controllers that allow you to not only stabilize the system, but also they're optimal in the sense that you can say, like, for example, I not only want to stabilize and I not only want to get the system to a set point, but I want to do it in a way that's efficient. I want to minimize the amount of fuel I use, or you know, you can prioritize, or I want to get there as fast as I can. And there's ways that you can craft the controller. You can tune it, basically. The PID controller doesn't really have a way to tune it other than just kind of arbitrarily turning the dials of the three parameters: the proportional Kp, the derivative Kd, and the integral Ki. So the proportional is it's a term where you take the error, you multiply it by a constant Kp, and then you add that into the output of the controller. There's a derivative which allows you to it's another constant, Kd. It's a control that allows you multiply that against the derivative of the error, and this allows you to slow down when you're approaching the set point too fast, essentially. And then there's the integral, which adds more correction when the error persists longer. So basically, it speeds up the longer you have an error, essentially, but it can cause an overshoot. And the original version of the slides, I had a little typo in there where I said that it actually reduced the overshoot. Well, in a way that's true, but the subtlety here though is that if Ki is too high, then you can have more overshoot. And I actually added some additional plots here too that show that a little bit later. Okay, so so the PID controller is Kp. So the time domain equation is GT, the output of the controller. G, by the way, is I think a kind of a common letter to use for the output of the controller. It doesn't have to be G, but it's just kind of conventional. So G of t equals Kp times E of t plus Kd times det dt. So you get the derivative, and then Ki multiplied by the integral of the error. And so the integral would start at, generally these are starting at time 0 and then up to the current time. So then you take the Laplace transform, which is super easy. Kp, just Kp times Et, just kind of the Et just drops out in that case. The derivative is you're adding an s multiplier, so it would be s times Kd, and then the integral is 1 over s, or s to the minus first power times Ki. So that, I love that, how, you know, when you go from the time domain to the Laplace domain, it just kind of simplifies it, drops out that stuff. And then so this would be fine by itself, except conventionally, typically, you want it to be a ratio of two polynomials. So I multiplied that, or I actually, sorry, I divided the whole. I multiplied by s over s, right, to get kds squared plus kps plus ki over s. So I multiplied the numerator and the right side by s over s. And then this is the PI controller. So you can drop optionally you can drop the integral and the proportional components. And I did that. I dropped the derivative in this case. All right, you can drop the derivative or the integral components of this. I dropped sorry, did I say that wrong again? You can drop the derivative or integral. Yeah, sorry, the derivative. So I dropped the derivative component. So now I just have the proportional and the integral terms. And that was, I didn't want to do that, but it was becoming a little too crazy in terms of simplifying it. So I just dropped it to simplify this a little bit. And so we ended up with an open loop transfer function. Now this slide is, I don't want to confuse you here. So the slide is a little misleading, actually, because the top I show the closed loop system. And you can tell it's the closed loop system because there's a loop in there, there's a feedback loop. But then I'm trying to, initially I want to just calculate the open loop transfer function. That would just be the open loop without the feedback. So that would be GC times GP. So GC is the controller, and that's KPS plus KI over S. So that's just the PI controller. And so it's cool. You just take that and you multiply it just right up against the plant, and the plant model is the one that I worked out from the physics, from the first principles. And so I set the mass to 1 and the coefficient of friction to 1 just to simplify this a little bit more. And then I just did some algebra and took those two ratios and multiplied them together, and I ended up with KPS plus KI in the numerator and S squared plus, times S plus 1 in the denominator. So notice how I left Kp and Ki. I took the constants M and B out, just by setting them to 1. I mean, I didn't take them out, I set them to 1. But I left Kp and Ki as variables because those are variables that I'm going to use to tune the controller. And then I calculated the closed loop transfer function. So you might say, why did you do the open loop transfer function first? Well, you could just jump straight into the closed loop, but I wanted to simplify the open loop because I know that the closed loop transfer function has the open loop in it, you know. So I calculated the open loop transfer function, I plugged it into the closed loop transfer function, and then, you know, you have to work out all the math here again to simplify it. And in this case, I did something that a little unstandard, non-standard. I think this is. I actually couldn't find a good way to do this in the literature. So the point, what I'm trying to do here is I want to come up with a way to set the proportional and integral term in a way that guarantees the closed loop transfer function is stable. So I kind of just I took the polynomial, the third degree polynomial in the denominator, and I factored it out in terms of a, b, and c, which would be essentially the roots, or the negative form. Minus a, minus b, and minus c would be the roots. So I decomposed the denominator in s plus a times s plus b plus times s plus c, and then from here I was able to come up with values for a, b, and c based on the coefficients in the denominator. So the coefficient in front of s squared is 1, so I know that a plus b plus c must equal 1. And then the coefficient in front of s is going to be ab plus ac plus bc, and I know that is going to have to equal kp, and then ki is going to be a times b times c. So now at this point, you know, we have some flexibility. You know, you can come up with any values as long as they meet these constraints, these requirements. So I just said, yeah, I'll just set A, B, and C to 0.25, 0.25, 0.5. That'll give me, those will sum to 1. And then I can multiply those together in various ways to get Kp and Ki according to the equations to the left. So that gives me a Kp of 3125 and a Ki of 0.313. I don't know if these are good values. All I know is, I mean, I know they're good in the sense that I'll have a stable system, but I don't know if they're good, you know, beyond that. Like, I don't know if this is going to be a great controller, but I know that at least they'll stabilize the plant. Now, I might have made this a little bit too hard. You know, I could have probably just guessed at these. But if I had guessed at Kp and Ki, I really would have never been able to know for sure if the values I guessed would result in a stable system, meaning that no matter what input you give it for the RF, you would get a bounded response. So I think it's better to come up with, at least be able to guarantee that it's stable. So then I get the impulse. So I plug in Ki and Kp, and I get my impulse response, and then I simulated it. I simulated a step, and that looks pretty good. Oh, sorry, the one on the top is the impulse response. The one on the bottom is the step response. They both look good. So notice that the step, you know, the impulse is kind of weird, because it's like basically what you're doing is you're saying that I want the set point to be 0. Then I'm going to pulse the step point up. And then I'm going to bring it back down to 0. And so what you're really seeing is, if I throw an impulse at the system, you know, how is it going to respond to that? And for a controller, it seems odd that, you know, obviously in practice you would never do that, because you'd never say, oh, I want the system to change the set point for, you know, an infinitely small amount of time and then back to 0, right? But this is a way to test stability, as I mentioned. And then the step response looks more like the way that you would use this thing in practice, right? You would say, I want the robot at 0. Now I want the robot to move 1 meter. And so so the step response is kind of a more of a realistic use case, whereas the impulse response is just a way to kind of torture test the system, essentially. Okay, so in this case, you notice that if we look at the step response, this is the sort of thing that we can expect in practice. So if this were a robot, for instance, you can see how the robot would kind of gradually, so first of all, there's a delay, right? So I tell the robot to drive 1 meter, and it takes it a while to get there, as represented by the rise time. So in other words, the robot basically wouldn't even hit the 1 meter mark until about 7 seconds. Essentially, that's where the yellow line, which is the actual output of the plant, meets the blue line, which is my set point. About 7 seconds it's going to take. And then the problem is that he's going to drive past 1 meter, and he's going to go up to about 1.2 whatever, just over 1.2 meters, and then he's going to drive back to 1 meter very slowly, and that's the overshoot. And that kind of stinks. I mean, imagine, I don't know, that would be I don't know, it's not a great robot, not a great robot controller, although it does, technically it's working. It's just not working really well. So you can tune this. I increase the proportional response to address the rise time, and then I increased the integral, which is supposed to drive the robot a little harder the longer it is away from its 1 meter destination, but that had the opposite effect, because that ended up increasing well, it had a deleterious effect, right? Because it caused it to overshoot more. So then I ended up let's see, I guess I don't show. At some point I decreased Ki to try to reduce the overshoot. So this is just an example of how to tune. I think you guys have seen this before, though, so I'm going to run through this. That's why I'm going kind of fast here. Okay, so that brings us to where we left off last time. So I mentioned at the end of the last lecture that when you learn classical control theory, like if you were to take the electrical 331 class, you would learn a lot about doing this kind of stuff. If they stay, I don't know if they do this, but if they stay in the S domain the whole time, or even if they get into the state space, the problem is that that is an analog. It's all analog. It's in the continuous time domain. And it turns out that the only way to actually build a controller that works in the continuous time domain is to make it analog, to actually design it as an analog circuit. Or there's other analog ways you can do it, like, for example, you could, there's ways that you can build things that sort of react in a way that's not governed by a computer, that are just react via physics. That rely on fluid pressure or heat or whatever, that kind of stuff. Or of course, you can build an RLC circuit made out of analog, passive components, and you can build a controller that way that would control the system. And that's fine, except most people, of course, want to use a computer to control. They want to use a microcontroller. The problem with that is that computers work in the discrete time domain. So what that means is that you're taking a computer that's in the discrete time domain and you're going to hook it up to a system, a plant that's in the continuous time domain. So from the perspective of the plant, the computer is going to have a sample time. It's going to have a sample rate, and so the plant is going to see the control signal as basically changing at discrete time points every sample time. So for example, I'm showing here that you have this analog signal, and the red line is the discrete form of that, and then the dotted lines are the sample points. And so the samples, every time you have a sample time, you'll output whatever the value of the analog signal is, and then you hold it. You hold it there steady until the next sample time, and then you hold it. So what you end up with is this kind of, looks kind of like a blocky, sharp edges. I don't know. It looks digitized, right? The red line. And so that's what the physical system, which is, if it's a physical system, it is an analog, system. It's an arm, it's a rotor, it's like a motor, it's an actuator. That's what it's going to be seeing from the controller, even though the controller is trying to give it a control signal. It's going to see this discretized control signal. Now likewise, you're going to have a sensor of some kind in the physical system that is going to be the feedback signal that feeds back to the controller, assuming, of course, you're doing a closed-loop controller. And so in a closed-loop controller, the input to the controller is also going to be discretized through the analog to digital converter. And so you're also going to see, in terms of measuring the state of the plant, you're also going to be discretized. So you might be thinking, well, what's the problem? Who cares? Why is this important? Well, this is actually really important, because if your sample rate is too low, you can have a controller that was making the system stable, but because your sample rate is too low, that can actually lead to an unstable system. And that's the whole problem, is that basically, depending on the thing you're trying to control, if your computer that's implementing the controller is not fast enough, doesn't have a small enough sample time, then it's basically not going to work. But the problem is the mathematics are not going to help you, because you'll end up doing the transfer functions, the closed loop transfer function. You'll check your poles. You can even run simulations. Everything will tell you that it's supposed to be working, but then you build it and it doesn't work anymore, because it has to do with all the time scales involved with the physical system and in the computer. So you might be thinking, well, come on, computers are, they're fast. They're fast enough to handle anything. Well, not really. There are high-speed systems that you want to be able to control sometimes. Like if you're trying to build a stabilizer for a camera, for instance, to eliminate the camera shake. For an active, sensor stabilizer for a camera, for instance, or any kind of high-speed system you're trying to, control, even like airbag deployment system, or high-speed avionics, like if an airplane is traveling, going fast. And also keep in mind too that, as I mentioned at the beginning of the class, we're targeting cyber-physical systems are usually low-cost CPUs. They're not often that fast. And not only that, but you may want to run other things on them too. So you might want to be time multiplexing the CPU itself. So you may not necessarily have the entire attention of the CPU. You may be only coming back and issuing control signals at a relatively low rate, because you're having to do other things on the CPU as well. So these are all things you need to consider. So the question is, how do we know if the sample rate is fast enough for a given system? Well, that's the question. So generally, the way that you deal with this is, in order to accurately model the behavior of a discrete system, you actually don't use the S domain. You don't use the Laplace domain. You actually are supposed to use the Z domain. And the Z domain is kind of like the S domain. It's the discrete form of the S domain. And so in a discrete system, you have a signal that's represented not as a function of time, but as a function of the sample number. So instead of t, you'll often see n. So you'll have x of n, for instance. And then these are kind of built up like you would a differential equation. But they're called difference equations in the discrete space. And so when you take a Z transform instead of an S transform of a difference equation, you end up with a system that's kind of similar to an LTI. It's also linear. It has to be linear and shift invariant instead of time invariant. And the shift invariant, these are just analogs really to the linear and well, linear is linear, and this means the same thing as it does in continuous. But shift invariant versus time invariant just means that shift invariant means you can shift the time, and it won't make in other words, none of the coefficients in the system depend on the sample number, essentially, is what shift invariant means. Now, the other thing that's a little frustrating about the Z domain, there's a couple things. The first thing is that determining whether a Z domain LTI is stable is different than an S domain. S domain is really easy. You just look for the poles, which is the roots of the polynomial in the denominator. So the poles, you find the poles, and as long as the poles are in the left-hand plane, the system is stable, right? So the Z domain is a little different. In the Z domain, a system, you can still calculate the poles, and Z domain transfer functions are also just a ratio of two polynomials of Z, but it's a little bit harder to determine if a Z domain system is stable. There's a few rules though. A system that have the poles that are close to Z equals 0, kind of to the origin, will settle rapidly. So now we're talking about how close these are to the origin, which means that we don't care whether they're in the left plane or the right plane at this point. We only care how close they are to the origin. A system with poles that are close to the unit circle will settle slowly. A system with poles that are on the right of the unit circle may have that are right on the unit circle, not to the right on the unit circle, may have a sustained response, or certain bounded inputs, it may have an ever-growing response. So basically, that means that if you're on the unit circle, you may or may not be stable. I know that sounds kind of wishy-washy, but that's how it is with the z-domain. You want to be close to the origin. And then systems with poles outside the unit circle will definitely be unstable. They'll have a response that grows exponentially. So basically, the deal with z-domain is you want to be on the unit circle, but ideally you want to be within the unit circle and close to 0 as possible. Okay, so let's look at some examples. Now this part, there's some aspects of this that are pretty cool. So let's go back to the original LTI that I made up as an example at the very beginning of the lecture. So I had u of t equals y of t plus dyt over dt times, or minus 6 times the integral of yt dt, right? And so we converted this to the S domain very easily by taking the derivative and basically making the derivative become sys, and the integral was 1 over s, essentially. And then in the discrete space, what would this be equivalent to? Well, here's where things get kind of interesting. So check this out. In the discrete space, the equivalent time domain, or in this case, discrete time domain, would be u of k. I don't know why am I using k now? It should be what did I say, n? I had n here. Yeah. Well, it doesn't. It's not a big deal. So k is the sample number, right? So u of k equals y of k. Now I get to the derivative. Well, how do you do a derivative in discrete time? Well, you look at the difference between y of k and y of k minus 1, which is the change over the last sample. And then for the integral, it's a summation from I equals 0 to k of y of k. So you can see that there's, that's how we go from, that's just generally speaking how you would go from continuous to discrete for a difference equation. Now, when we convert this to z-domain, though, it's also a little wonky, because the derivative is converted not just to z as you would with the S domain. It becomes z minus 1 over z. And then you multiply that against y of z. And then you also have to multiply that by 1 over ts, which is the sample time. Now, if you're just designing, if you can abstract out the ts if you're just if everything is sort of in units of like clock cycles or whatever your sample time is, but this is kind of the formalized way that you would do the conversion, is that you would multiply that by 1 over ts, and then for the integral, or in this case the summation, that would become z over z minus 1 times y of z. Okay, so notice now, again, we took the variables, or not the variables, the functions, or the signals, I should say, u and y. They are now capitalized. Instead of being of k, they are now of z. So we've switched it to the notation for the z domain, and then the derivative became z minus 1 over z, which is also called the first difference in the z domain. And then the integral, or the summation, was z over z minus 1. Okay, so so in this case, I'm going to just assume that the sample time for the time being is 1 second. So I'm going to set ts to 1, and so we end up with that. And then I can come up with a transfer function much the same way I did in the S domain, which is by taking y of z and moving it to the the denominator of the left-hand side, you know, under the output, y u of z. So but by doing this, I've now decided that u is my output and y is my input. And so the transfer function becomes 2 minus z to the minus 1 power minus 6 times z over z minus 1. So that's the function. And of course, you can put this into a proper ratio form by just manipulating, you know, multiplying both sides by z over z rather. Okay, so let's talk about this first difference thing. So what is actually going on here? Why z minus 1 over z? Why are we doing this instead of just z like we have with the S domain? Well, if you look at z minus 1 over z, that's equivalent to, you know, 1 minus z minus 1, right? If we just take, you know, we break it up and say it's z over z minus 1 over z, which is equivalent to 1 minus z minus 1. So what is really going on here? What does this mean? Well, actually, it's kind of neat because it turns out that z minus 1 is actually representing the last sample, the previous sample. And 1, or z to the 0th power, is the current sample. And that makes a lot of sense when you think about it, because that's really all we need to know here with the derivative, is we want to know the value of the current sample minus the value of the previous sample to get the difference, the change, in the first difference, okay, which is the difference between the two most recent samples. Now, you might be thinking, okay, well, this actually gives us a way to implement this in code. This is starting to look more like a program you would write then. So you, like, for example, if you were writing a for loop, you could just say, you know, look, the value of this would be the current sample minus the last sample, which is kind of brings us a little closer to, like I said, to an implementation. Now, what about the integral, though? The integral is a little goofy. So the integral is z over z minus 1. How does this work? Well, this one is kind of neat because you can do this thing where you can do a polynomial long division. So if you take the denominator and you make that the divisor, and then you take the numerator, and that's, of course, the dividend. So you take z minus 1 divided by z. If you work it out like a long division, then you would put a 1, and then you would, on the top, right, of the long division bar there. And then you would then multiply that against the divisor, z minus 1, and then subtract the divisor from the current sort of the remainder, right, or whatever initially it's whatever the dividend is. And from that, we'd end up with basically a remainder of 1, because the minus and the minus, the fact that we're subtracting, and the fact that was a minus 1 that we're subtracting, that the minus signs cancel out, give us a positive 1. And that basically just gives us a remainder of 1. And of course, the remainder then would be shown as the quotient here would be, the quotient would be 1, and the remainder would be 1. But then, of course, you would take that remainder, and it would be 1 over z minus 1, right? The original denominator. So that gives you, basically just gives you 1 plus 1 over z minus 1. Well, that's kind of cool, but I mean, that doesn't get us any closer to what we want, right? We're trying to figure out what this means. Well, you can do the same thing again. We can take the fraction 1 over z minus 1, and we can work it out in a long division. So z minus 1 divided by 1. I want to figure out what to put in there on the top there as my quotient. So I'll put z minus 1. I'll multiply that against the divisor, which is z minus 1. That gives me 1 minus z minus 1. I will then subtract that, and I'll get a remainder of z minus 1, which means that the dividend is, or sorry, the quotient rather is z minus 1, and the remainder is z minus 1, and I will put that remainder over the original dividend, z minus 1. So this is basically works out to be, allows me to convert the 1 over z minus 1 to z minus 1 plus z minus 1 over z minus 1. And then you can repeat this again. Z minus 1 divided by z to the negative first power, I work this out in long division, so that would be I would put z minus 2, z to the negative second power, on the top of the divider bar, and then I would then multiply that against my divisor. That would give me z to the negative first time minus z to the negative second, and I would subtract that, and I would get a remainder of z to the minus second power. And so that would be my remainder, which I would put over the divisor, z minus 1. And so now I've further expanded this out to z to the minus 2 plus z to the minus 2 over z to the minus 1. Now you might be able to, you might see that there's a pattern growing here. So basically, this is going to continue endlessly. If I keep doing this over and over again, repeatedly, I'm going to have 1 plus z to the minus 1 plus z to the minus 2 plus z to the minus 3 plus z to the minus 4 plus z to the minus 5. And this will literally just go forever until I get to basically the first sample. Well, that makes sense, though, because that's exactly what the summation is doing, right? So if I'm calculating a summation, a discrete integral, my goal is to add up basically all of the values, all of the samples that have occurred from now back to, you know, the beginning of time, basically. So in a way, if you work out this, I mean, if you assume, of course, that z to the minus n means n samples back, and then you work out the algebra of z over z minus 1, you can see how this actually does, in fact, represent an integral, or a discrete integral, which is a summation. Okay, so now let's go back to the example I had. So in this case, I now have a z domain transfer function that matches the same form as the one that I made up earlier. So this is 2 minus z to the minus 1 minus 6 times z over z minus 1. I think that's the same numbers I had with the S domain example. But anyway, it's example. Okay, so so I am going to basically start working on this to convert this into a proper form. So I'll multiply both sides by z minus 1, and then I can get both sides of the equation by z minus 1, and that allows me to get the right-hand side of minus 3 plus z to the minus first power minus 4z, and then I divide that by z minus 1. So this ends up giving me a proper sort of a ratio of two polynomials of z, and then of course I can multiply the numerator and the denominator by z, and get out the z to the minus 1, make the minimum power of z 0. And then and then I wanted, so in this case I just swapped the numerator and the denominator because I wanted the transfer function to be y of z over z of z. I wanted y to be my output and z to be my input. In order to do that, I had to swap. I had to get two of the left-hand side correct. Okay, so so this gives me a transfer function, and I factored. So I took the 4 out of the leading 4 out of the denominator by multiplying the numerator and the denominator both by 1/4, and then I factored the denominator. So I had z squared plus 3/4 z minus 1/4. So I factored it. So now I have z plus 1 times z minus 1/4 in the denominator. And now I have my poles. So I've got poles at z equals minus 1 and z equals 1/4. Okay, well now I have an issue because I've got a pole at minus 1. That's on the unit circle. And according to that, according to the description, this is the kind of the wishy-washy version where it says, may have a sustained response. So this may or may not be stable. So that's not so good. Let's find out if it is. So how do we find out? Well, so actually I'm going to revisit that. Sorry. I'm going to switch topics here to the Tustin Transform. So so switching topics a little bit, we'll come back to that. So how do the question is how do you take a plant that is in the S domain and it legitimately is in the S domain because it's, typically it's a physical system, right? It's in the continuous time. And now I want to design a discrete controller inside of a CPU to control it. And of course, I can do that, I can do everything in the S domain, but then I have no guarantee that I've got a controller that will even be stable, because it may turn out that my time step, my sample time, is too long for that system. So one way to do it is to, and the way some people actually do it in the industry, is they just assume that I'll just design the system in the S domain. So I'll basically do what I did back here. So over here, notice how I had an S domain, actually down here, I had an S domain transfer function, and it's pretty straightforward, as you can imagine here. This S domain, I can convert this to the equivalent Z domain, just as I did right here. Like, I can go from the left side here to the right side, right? I can just use the same coefficients basically, and then convert the S to Z, and then I can convert S, which represents a derivative. I can make that Z over Z minus 1 over Z, and I can take the integral, which is 1 over S, and I can substitute that for Z over Z minus 1. That's one way to do it. And it turns out that works sometimes, but there's no guarantee that will work, is a problem. If you have a slow enough system, it'll work, because basically it'll mean that the processor is fast enough to make it not be an issue. But a better way to do it would be to convert the S domain transfer function that is modeling the plant. You can convert it to the Z domain. And you can do it. And there's actually a few different ways to do it. The most widely used way to do it is through the Tustin Transform. So this will take an S domain transfer function, convert it into the Z domain. It'll discretize it using something called a trapezoidal integration, essentially. And there's a way that you can derive what this all means, but in this case, I'm just going to give you the procedure for how to do it, instead of actually explaining why it does that. But the answer here is you take everywhere S appears in the continuous S domain function, and you replace it with 2 over t, where t is the sample time, multiplied by Z minus 1 divided by Z plus 1. So for example, if you have a transfer function of y of S equals 1 over S. Now, what's 1 over S? Oh, that's the integral. That's just the integral. That's an integrator. Okay, so I expect it to behave like an integrator, right? Okay, so then I can take the 1 over S and plug in the Tustin transform, and of course you got to work out, you got to work it out and make it a a polynomial ratio of 2 polynomials, which I did here, and I get Z plus 1 over 2Z minus 2. So this is the Z domain, essentially integrator, right? So then I simulated this over the step response. I grabbed a step response and I showed it. I'm showing it here on the right, and this is pretty interesting. Also, notice I set t to 1 too. I forgot to mention that. Sorry, t is 1 in this case. The sample time is 1 second. So if you look at the plot, you can see that the blue line is the input to the system, which is the step response. It goes from it starts at 0, and then it transitions from 0 to 1 at time 1, and then it stays at 1 until the end of the plot there, which is at 10 seconds. So from 0 to 1, it's 0, and from 1 to 10, it's 1. So that's a step, and then the yellow line is the continuous time response, which technically it's not continuous because I ran this on a digital computer, but it is it's an approximation of the continuous time response. And then the orange line is the output from the discretized transfer function, the z plus 1 divided by 2z minus 2. And so check it out. It's doing exactly what you'd expect it to do. It's like a little staircase. It kind of hugs the continuous space, and it changes every second. So that looks basically what you'd expect. Okay, so let's go back and let's do this to our physical model of moving an object, the one that we came up with from the first principles, moving an object. So remember, if you recall, that was had a transfer function of 1 over ms squared plus bs, where again m was the mass and b was the friction. And so I'm going to convert this to the z domain, convert it from s domain to z domain by doing the Tustin transform. So you take the 2 over t times z minus 1 over z plus 1, and I substitute that in for s into my physical model. And so you got to go through all the math. I said the t to 1 second again. So I'm not gonna go through every step here because I'm running a little short on time. But I worked it out. Hopefully I didn't make any mistakes here in my algebra. I don't think I did, because then I simulated it and it looks good. But notice that here the poles are at 1 and 1/3. Well, once again, I have a pole at 1, which is on the unit circle, which is kind of the undefined for the z domain in terms of stability. Now, we already know this is an unstable system from our s domain analysis. So how would I implement this thing, by the way, if I wanted to design a model for this in in C code, for instance? Now think about this. What are we doing here? What am I saying? What I'm saying is, how can we use this? How do we go from a differential equation, convert it to the S domain, and then convert it to the Z domain through the Tustin transform, and then convert it to C code, run the C code, and in that C code, we now have a model for the physical system that I originally developed through, essentially Newton's laws, right? How does that work? Well, this is the pretty cool part. So if I take the, by the way, the transfer function is 1/6 z squared plus 1/3 z plus 1/6 divided by z squared minus 4/3 z plus 1/3. That's the transfer function in the z domain. Now I want to do this in C code. I want to build this out in code. Well, the problem is that I need to get it into a form that I can then convert to C code, to program code. So to do that, if I multiply the numerator and the denominator by z to the minus second power. Now, why am I doing that? Because I don't want any positive powers of z in here. I want to get everything to be, all the exponents should be 0 or less. Okay, because obviously when I design this, I can only use samples that I've seen in the past. So I do that. That's pretty easy. And then I have to change the form a little bit to where I can get the output, which is y. Remember, the output is y and the input is u. So I need, if I'm going to convert this to C code, I need y on the left side of the equation, and I need all of the stuff that's a function of u on the right side of equation. But what about the past values of y? Well, those will also go on the right side of the equation. So I need to I need a way to calculate the current value of y as a function of the previous values of u, which is the input, as well as the previous values of y, the previous output values, the history. And I can do that as long as all my z exponents are less than, that are less than 0 in the case of the y, and then less than or equal to 0 in the case of u. So again, I got to work through all this math, and this is really just a matter of, okay, so I got to get, I got to take the u of z, multiply that by both sides of the equation. Then I got to get the denominator of the right-hand side and multiply that against both sides of the equation. So then I end up with what I've got there. And then I got to get y of z by itself. So I get that by itself on the left-hand side. Everything else is on the right-hand side. And then then I'm basically done, because at this point I can convert this from the Z domain back to the time domain, or the discrete time domain anyway, by basically just doing what I alluded to earlier. I didn't directly say this, but if you do an inverse Z transform to the time domain, you would then just say Z minus 1 times U of Z. Well, that's the previous sample of U. And Z minus 1 times Y of Z, well, that's just the previous value of Y. So now I've got literally essentially a line of code. Really, this just translates directly into code, because I'm just basically taking the current input value and multiplying it by 1/6, and then I'm taking the previous input value and multiplying it by 1/3, and the the current input value times 1/6, the previous input value times 1/3, 2 input values ago times 1/6, and then I'm taking 4/3 and multiplying that by the previous output value. That's pretty cool, right? The previous Y. Well, I know what that is. It's whatever I output in the last sample. And then minus 1/3 times 2 output values that I generated ago. And then I sum all this up, and I get the current output value. So, so how's that look? Well, basically, I could do a step response and look at both the Z domain and the S domain representations, and they work out. I showed them here simulated from 0 to 10 seconds, and you can see that they both look right. Now, notice how in the S domain, it's kind of funny. You know, the S domain looks kind of linear when it starts to go up, but you notice at the bottom here, there's a nice little curve as it ramps up. And of course, in the Z domain, you know, I don't have that. It's all blocky blocks because it's discrete. But you know, this is the Z and the S domain version. So that would be basically how I would take the physical system and model it in like in a program. Okay, well, how about then program the controller, the PI controller? The PI controller is I can take the PI controller and I can essentially just take Kp and Ki and multiply Ki times the integral Z, which is in the Z domain, is Z over Z minus 1. Okay, and then I can build a Z domain transfer function for the PI controller. It's pretty straightforward. And then I can calculate my open loop transfer function in the Z domain as I did in the S domain by multiplying those guys together. And then you know, and I don't show it here. I'm not showing it here, but you would then have to take this and put this into the closed loop transfer function and build that up. And then once you do that, you can do a step response. So this is a step response. So this is the same. So basically, the idea is this is supposed to be the same controller I had for my little object moving system as I had with the S domain, but now it's in the Z domain. And now in this case, I didn't do anything fancy like choosing Ki and Kp to guarantee stability. I didn't do that this time. Now I got a little bit lazy here, and I just said, okay, I'm going to set Ki to 1 and Kp to 1, and that may or may not give me a stable system. I didn't validate that through checking the poles. But I did it, and I simulated it, and you can see that it worked. I mean, it seems like it worked. We've got the set point. Now I had to, in order for this to look good, I had to increase the time scale from 10 seconds to 40 seconds, because at 10 seconds it didn't look like it was working. But when I expanded out the amount of time, I get a nice you know, convergence there. And again, this is a t equals 1 second. Now I can always decrease the sample time, increase the sample rate, and this will look better. But this is kind of a 1 second sample rate, so it makes sense that at 1 second sample rate, this thing would take 40 seconds to work. Okay, so what about, you know, trying to fix it up a little bit? You know, instead of changing the sample rate, I decrease the integral, the Ki, the integral term, and that actually made it stabilize a little faster. The overshoot is a little bit better too, actually. Not much better, but the convergence time is better. And what happens if I make the I 0? Well, actually, that looks the best. This is just a proportional control. So in this case, proportional control for this system was actually pretty good, although keep in mind that I'm doing this over 40 seconds. If I were to plot this over 10 seconds, which is the original, when I did it in the S domain, I was over 10 seconds. Of course, it would look it would look a little worse because you wouldn't see this period from 15 to 40 seconds where it kind of converges on the blue line. So yeah, this one looks pretty good. And then I tried setting the KP to 0.5, so I brought the proportional down a little bit, and you can see that that made the rise time worse, but it limited the overshoot. The overshoot is less, but the rise time is worse. So I traded off overshoot for, I mean, the rise time is worse, but the overshoot is better, right, by doing that adjustment. So this is all just kind of tweaking these parameters manually. And so that's all we've got. So one thing that I was planning on showing in this lecture, and I didn't get to it, and I was running out of time. I don't want to make this whole class a controls class. But one of the things I wanted to show in here was that you could have a stable system, and if you convert it directly into a discrete time and you have your sample rate is too long, then it could destabilize it. Obviously, I didn't show you that here, but you can imagine that if your sample time is too long, it's obviously going to present problems, especially considering how, you know, the stability criteria for the Z domain is different from the S domain. So, you know, for example, you can have negative poles in the Z domain, but if they're outside the unit circle, you have an unstable system, whereas in the S domain it would be stable. So there's a lot of stuff, you know, you can imagine that you have to consider when designing these controllers, depending on what the performance is of your microcontroller. But you know, I didn't want to get too far into this. I want to just give you a taste of control theory. So that's all we've got for control theory. In the next class, I'm going to switch topics to real-time scheduling. And the reason I'm going to talk about real-time scheduling is because obviously, if I'm doing a controller in a processor, I need to be able to issue these control commands at a fixed interval, and I can't miss any deadlines. I need to be able to guarantee that I can achieve the sample rate that I've promised, or that I was targeting in the design of the control system. And so it turns out that real-time guarantees and real-time scheduling can be challenging for a variety of reasons. So I'll get into that in the next lecture. In the meantime, I'm going to stop a little early. I want to give you some time to work on quiz 3, which is available online now and will be due on Wednesday. Yes, thank you, Ben. Yes, the reason I ended here was because this is all the material you need for the quiz. The quiz covers all the material I covered on control theory, and so everything I showed in the slides is the kind of questions I'm going to ask you about. Okay, great. Are there any other questions? A little bit. There's a couple questions that require you to work out math. Yeah, but it's all you know, it's all algebra. That's the thing I like about this stuff, is that it's, you know, you're doing differential equations, but you're doing differential equations, but you're reducing them down to algebra, which is the cool thing. Yes, I can update the slides. I think I always tweak these slides, so I'll be sure to update them. Yep, no problem. I'll upload the slides when I upload the lecture video a little bit later, after the lecture video updates. And by the way, if any of you guys ever want to access the lecture video, I mean, I don't think this applies to anyone who's here, because obviously you guys watch the lecture live. But just for the record, if you go to download the lecture off of Dropbox and it's not there because I haven't posted it yet, you can always get it on Blackboard. Blackboard will post it, you know, I think within an hour or so, it comes up on Blackboard. And in fact, it's better on Blackboard because you get the chat log too. So, but it does take me a little while because I have to download to get it on Moodle. I have to download it and then upload it and modify the Moodle page and all that stuff. So it usually takes me a few hours to do that. Okay, well, great. If you have any other questions, feel free to email me or the TAs. And remember, we have no class on Monday, so enjoy your day off. The quiz is not due for a week, so you got plenty of time there. And we don't have any new programming projects up yet. We'll probably be announcing those soon. And as I mentioned, the exam will be on the 24th. Which is, I guess, 2 weeks from today. So that'll be the first exam. So we'll see you then. Thank you, everyone. Oh, I don't know if I might have. I'll try to do a review for the exam, but I'm running a little late because I have to cover. I want to cover the real-time scheduling stuff. I'll try to do a review. Yes, I'll try to do a short review, but it won't be a whole class.